So in this tutorial, we are going to look at the relationship between voltage and current for two different devices, just like you did for your lab. You should already have a pretty good idea of what the relationships are, but we want to extend that and look at some insights and introduce a very important measurement in a circuit called resistance. The title of this lesson, and if you look on your note sheet, is Ohm's Law. Ohm's Law is probably the central idea in all of circuits. So this is very, very, very important. It's fairly straightforward, but if you have any questions, any details that you're not quite sure about, make sure you ask. All right, so let's start with a graph, a hypothetical graph, where we plot voltage across a load and the current that goes through it, okay? So the schematic would be, here's my voltage source, I have some load here, and I complete the circuit, and then I measure, I put a voltmeter across it, and I put an ammeter in there. I know that doesn't look very good, but that should look just like the schematic you had in your lab. All right, so we see that when we look at the points, they form a pattern like we'd expect, and we see that it's definitely a linear. In fact, it's linear and proportional. Okay, so that's important to know. In other words, for this particular load, which I believe is a ceramic, hopefully I have it there, that we see that if you double the amount of voltage, you'll get double the current. Now, in this particular one, I've reversed the voltage and the current for reasons that I knew beforehand. In your lab, you might have put voltage down here and current here. So your slope will be the inverse of what I have or what I would have done. But that doesn't really change the fact that they're going to be directly proportional to one another. So if you want twice the current in a load, through a load, you would double the voltage. So if we calculate the slope of this, so if I take 2 points, let's say right here, and I take the 0, 0 one, I'll do the easy way up. I've got 100 minus 0 volts divided by 2 minus 0 amps. So I see that I have 50 volts per amp. And that's constant throughout for any voltage. All right, so for every ampere that I want, I need 50 volts of current. And we're going to come back to that in a little bit. So let's continue looking at analyzing this graph. Okay, so what we say is any load resistor that has proportional relationship between voltage and current obeys Ohm's law. Georg Ohm was I don't know if he was German or Austrian. Anyway, back in the 1800s, discovered this law, and it's very important. So anything that obeys this is said to be ohmic. So it's a descriptor, meaning any resistor that obeys Ohm's law, which kind of implies that not everything obeys Ohm's law. So if you're ever asked a question, is this ohmic or not, it means that the ratio of voltage to current is constant. Okay, and so that ratio of voltage to current, and that's why I chose to put voltage on the x or the y-axis, represents an important property of the resistor. In other words, if we had done this with a different load, we might get something that looks like that. Or we might get something that looks like that. In other words, we get a directly proportional relationship, but we have different slopes. So the slope tells us something about the circuit. Okay? And that is the property of the resistor called resistance. And we give that a symbol, capital R. Okay, so in this particular case, it's the slope of the graph, but really what its definition is the ratio of voltage to current. So resistance is our fourth measurement of the circuit. We have voltage, current, power, and now we see that resistance of the load plays an important role in all this. All right, so since there's a linear relationship between V and I that tells us the resistance of the load is constant, and so from the graph, that means that our resistance is 50 volts per amp. Okay? Now another name for a volt per amp, in other words, the unit for resistance, is called an ohm. Appropriately enough, after Georg Ohm, and it has a funny looking symbol. Looks like an upside down horseshoe. That's the Greek letter omega, actually the capital omega. We did lowercase omega for angular velocity. Alrighty. So we can now make equations from this graph. And we're going to write 3 equations. They're all the same thing, just rearranged. From the graph directly, we can do y equals mx plus b, which says that the voltage drop across a load is equal to the current times the resistance. In other words, y equals m times x. We'll talk about that voltage drop idea versus something called EMF later on, okay? But it's a very simple relationship. If we go by the slope, we can see that the slope, which is just resistance, is by definition a ratio of voltage to current. Okay, so if I ever give you a resistor and I say, hey, find this resistance, hook it up in the circuit, measure the voltage across it, measure the current across it, and at that particular case you have the resistance. Now whether it's ohmic or not, you'd have to do a series of points to see if they follow a directly proportional relationship, but that's a different question. And then lastly, and I would consider this maybe the most important way to write it, is that the current in a circuit is equal to the voltage divided by the resistance. And this is causal. Okay, so what do I mean by that? I've used that term here and there throughout the year. Is that saying I depends on V, it's proportional to V. You found that out in the lab. Okay, and what it's also saying is if I plot I as a function of resistance, I see this an inverse, and so it's going to drop. On the other hand, resistance does not depend on V and I. In fact, it was constant throughout the lab, so if we change voltage, we get a proportional change in current, at least for something that's ohmic. We're going to learn eventually that resistance depends on something else altogether, but it is equivalent to the ratio of voltage to current. So if you recall in some of the data in your lab, you had sometimes like 1 amp, 1.5 amps maybe, or a few tenths of an amp. And we saw in a prior lesson that a few tenths of an amp passing through you is dangerous. In fact, it can be deadly. More than an amp would be like cooking inside. So why weren't we worried about it? Right? If there was 1 amp going through the light bulb, why were we not worried about 1 amp passing through us as we were touching the wires and connecting and disconnecting? Well, that's because if you want to become part of the circuit, your body has resistance. And the resistance of your body, especially your skin, is way, way, way higher than that of the loads you have. So just because there's 1 amp in one part of a circuit doesn't mean there's going to be 1 amp everywhere. It depends on the resistance of that part of the circuit or whatever connects to that part of the circuit. So, for example, your dry skin is roughly, give or take, if you order magnitude, 100,000 ohms. So if you place 10 volts across 100,000 ohms, you're going to get less than a milliamp of current. You're not going to feel it. If you have wet skin, then your conductivity goes up or your resistance goes down, and so let's say it drops down to 1,000 ohms, especially if it's salty water. Now, for a voltage source, things can become a little bit more dangerous, but for what we were dealing with, 10 volts divided by 1,000 ohms, you're barely going to feel it. On the other hand, if we have a light bulb, okay, that is rated for 120 watts, we can figure out the resistance through a series of calculations, and I'll do that right now. In other words, we're assuming this is plugged into a 120 volt source, standard US. So if I know V and P, I can find out the current. The current is power divided by voltage, all right, and that would be 120 divided by 120, that's 1 amp. So if I want to find a resistance, I would take, by definition right here, voltage, 120 volts divided by 1 amp tells me that that's 120 ohms. So we see that a normal light bulb is a fairly low resistance compared to wet skin or dry skin. Alrighty, let's turn back to something we've seen in class, the hot plate. And so when we turned it on the other day, we saw that it drew 5.1 amperes of current. There's I, and it's connected to an outlet, and so we know that that is 120 volts. So if I want to know the resistance, that's pretty straightforward. Resistance is 120 volts divided by 5.1 amps, and that gives us around about 23.5 ohms. And the reason that's significant, we want to look at the big picture. We plugged in the hot plate. It was designed to give us roughly a power of 600 watts. It was designed to be plugged into a voltage of 120 volts in the US. So if we want to get 600 watts of power, then it means we need to draw a certain amount of current, 5.1 amps. Well, how do we get 5.1 amp currents if we're designing this? Well, we must design it so that it has a resistance of exactly 23.5 ohms. And that's an important concept to remember. So you build something based on a resistance, you plug it into a particular voltage source, knowing you're going to get a certain current, which will give you a desired power. And that's how all four fit together. All right, so let's turn our attention to the light bulb. So if you did the light bulb, if you got good data for it, what you will see for the light bulb is that it follows a curve that looks like this. If you put voltage on the y-axis. If you guys put voltage on the x-axis, then it might look something like that. Okay? Either way, what you should recognize is that it's not a straight line. And therefore, it's not ohmic. So I'm going to jump down to C. So does the light bulb obey Ohm's law? The answer is no, because it's not linear proportional. However, we can look at this from a different standpoint. We can look at the resistance at various voltages or currents. So for example, what's the resistance when the current is a half an amp? So I go over to half an amp. I don't find the slope of this. I know in a previous problem that we said that the slope was equivalent to resistance, but that's only when you have an ohmic device. In this case, we'd use the definition of resistance, which is the ratio of voltage to current at that point. So our voltage would be roughly 5 volts for a half an amp, and that would be 10 ohms. Now if we go to a different current, 2 amps, go up to here, drop over, we see, I didn't draw that very well, our voltage is about 34, so V over I is 34 divided by 2 amps, which is 17 ohms. So we see that our resistance is changing with current. That's non-ohmic, okay? So a non-ohmic device is essentially something that A, looking at a graph, isn't linear proportional, or B, its resistance changes as the current changes. And then we'd ask the question, well, why does the resistance change with current? All right, and eventually the short answer is because the bulb gets warmer and warmer and warmer, and we're going to learn that temperature of a resistor affects its resistance. But that's another topic for another day. All right, lastly, in a few minutes I want to start on this. Power generated in a resistor. So if we again draw a schematic, I have an input of energy, I go through a load that we can now call a resistor R, and I deliver a certain amount of power, and the power is developed here. So it makes sense to develop an equation that tells us the power output of a device based on its resistance. Okay, so that's not a hard derivation to do. So let me go back. Although somewhat simplistic, there's two ways you can look at a resistor in a circuit. It controls the amount of current. In other words, if I want a very little current in a circuit for whatever reason, I put a high resistance in it. If I want a lot of current, I have low resistance. The resistor is also usually the load itself. Thus, that's where the power output is generated. Okay, so as I was saying earlier, it makes sense to develop an equation that relates power output to a given resistance. R. Okay, so let's do it. We already know that power in a circuit is voltage times current. But according to Ohm's law, we also know that current is equal to voltage divided by resistance. So if we combine the two, we get a very simple equation. We take out the I, put in V over R, and we get P equals V squared divided by R. Okay? And if we do another substitution, we also know from Ohm's law that voltage drop across the load is equal to the current times the resistance. So if I substitute this into the V, then I have I times R times I, or I have P equals I squared times R. So now we have three equations that can tell us the power in a circuit. We can do voltage times current if we know both those, or we can do voltage squared divided by R, or we can do I squared times R, all depending on the information that we have, which is pretty nice to know. Okay, so let's do one last problem, assuming I can scroll down. Apparently I can't, it's frozen here. So what is the resistance of a 150 watt light bulb if it's designed for a 120 volt outlet? Now in a prior problem, I did this in 2 steps. Now I can do it in 1 step. I have P, I got V, I'm looking for R, so the equation I'd want to use would be right there. So I'd say 150 equals 120 squared divided by R. So R is going to be let's see, 120 squared is 144 with 2 zeros divided by 150. So that looks to be not quite 100 ohms, but let me double check before my time runs out. All right, so that's 96 ohms. And then I'll leave you with one last question. If the resistance of a load doubles, what happens to its power output? So I want you to come in with an answer for that tomorrow.